So that's it. So you should be able to know that if you first of all, if you have not loaded the package into R, you will not have access to the data. And secondly, you may load it, in other words, use library or take it at the package, but it will still be telling you that the data set is not available. Then it means you have to use the data function to call the data into your working directory to have access to it. Okay. Now, so as I said, this is your assignment. So now I did this and I got this. This is what Bartlett test of homogeneity or variances. So this is testing whether the ANOVA assumption is satisfied. Is that okay? And you look at the p-value. What is the p-value? Very small. Yeah, you need 15 zeros before a 2. So it's more or less. So you reject the null hypothesis. And what is the null hypothesis? Equality of variance. The homogeneity means they are the same, right? They are similar. So it means the variances are different. All right. So this is not something that you can use ANOVA because it violates the ANOVA assumption. And if you want to see this, you can also do a box plot with the same data. The box plot will reveal. So this one I need more because there are so many. Let's Control R. No, Control Enter. It says margin. Look at this error. Error in plot new. Figure margins too large. You see where my plot should be is like this. It's quite small, so I will not be able to plot over there. So what I need to do is to enlarge it, okay, and redo this, and redo the box plot. Remember that it's like 17, okay? So 17. We did this, right, last weekend. So if you look at this, you see there are so many outliers. Look at this one, and this. Can you say the variations are the same? No. So that's why we go. So this is not an example we should be using ANOVA to do because it violates it. The visual plot should tell you that this will violate normality, right? Isn't it? Completely. You cannot say that this data is normal when it has some unusually large observations. And how do you check for normality? There are so many tests in R for it. You can use the easiest one will be the Shapiro-Wilk test. Okay. So if you do Shapiro, you can look at it. So this tells you, I mean, that the insurance claims paid in each state, right, may not follow necessarily normal distribution. And if you want to check it, as I said, you can use Shapiro. So if you do Shapiro test, okay. So you can look at that as well, Shapiro-Wilk normality test. Okay. So there it is. How do you do this? Well, I think that won't work like what we did. So you have to, let me copy this and send it somewhere. What you need to do is that you can't use a formula in the Shapiro-Wilk test. So I'm going to do it for you to see. You see the box plot, it was easy. I just say plot this per what? How should I put it? Per state, right? I cannot put this here in the Shapiro because the Shapiro just take X. Remember, it says X is what? Numeric vector of data value. So if I put in a formula, it won't work. Look at it. It tells me that error in Shapiro, so and so and so. Unused argument, data is equal to auto claims. Okay, because it doesn't. So if I want to do this, then I need to take each That is where your knowledge of data structures comes in. I have a data frame, okay, which has one column will represent the state, and then I have the amount paid. So it means I have to select all states with state 1, and then I check whether the data set is normally distributed. Then I go to state 2, I check whether the data set is normally distributed, and so forth. Is that okay? Is it okay? So that's how you have to do it. And that there will be so many methods you can use, for example, with and so forth. So you can check the function with, and is a subset. There's also subset and so forth. You know, in R, nobody can teach you R throughout. You have to explore. Okay, you have to explore all the time. Now, the easiest way out is that if I want to get this state, I can say, let's say state. Okay, let me say I want state 1, right? Then what I'm going to do is that I'll call auto claims. Auto claims. Now, auto claims are states, right? Okay. But I need to know what are the states. Let me just do head of the data we are dealing with. What does it mean? If I say head this, what am I going to get? I'll get the only the headings. Oh, you are using the head to the what? No. Head. What about tail? Because if I get head, I can get tail as well. The first 6 observations. So if I want to see how a data set looks like, I can use the head. It will give me the first 6 observations. If I use the tail, it will give me the last 6 observations. Yeah. So this is how it looks like. So what it means is that you see state 14, state 15, and so forth. So each state, I want to know what was paid. So how do I select, let's say, all observations in state 14? Well, it means that I'll call this, right? And I'll say equal to. Remember this, when we say equal to, it means you are checking whether there is equality. Okay. So it means if I call this state 14, state 14. So if I do this I have about 6,000 observations. So every one that, well, you remember that the first observation is a state 14 observation. So you see that one is true, it will be true. You see, but the second one is not. Look at the C's one, it's not. So all of them are false. Do you get what is happening? So what I'm checking is that check all the columns or the state. If a state is equal to 14, it will be true. I'm checking for equality. Okay. Come on. So we are selecting each state. So if we put this in remember we did something, right? So we are going to start with, okay, using such that you will get 20 million for state 4. And then one engine you get that of 50. And so and then once you put this inside the auto play, okay, with then it will select only payment from state 14. And then after that, you can check whether this one follows the money. So let's step 1, and you are signing. Handing over. So we just use Sapiro. Yeah, come. They haven't started. Okay. So it's all. I wasn't using. Yes, I'm not assigning them. So here, what I want to let me just give a comment. Extract all state 14 observations. So all observations for state 14, that's all I want to extract. So what do I have to do? First of all, I check state equal to 14. That is logical. So it will give me true or false, right? Okay. Remember our subscripting. So then I'll come to auto claims. Okay. Then subscripting, you use this, right? Okay. So I'm saying every row containing state 14, select it. Is that okay? Which means each row with true will be selected. Each row with false will be omitted. Is that okay? So it means I can put this one in. And remember that this is a data frame. So you have rows and columns. So there must be a comma within the bracket, within the square bracket, right? So I put the comma. And where will the rows be? Before the comma. If I want to select columns, it will be what? After the comma. So I put this expression here. Now, if I do this and I run it, it means it will select only state 14. And you see, so the 6,715 position is an observation from state 14. Similarly, 6,535 is also from what? State 14, right? And so forth. I can scroll up and so forth. So you see, it is selecting only state 14. Is that okay? Is that okay? So this is state 14, all observations, right? Okay, so I can name it like this, state 14. Now there it is. So now this becomes a data frame which contains only observations for what? State 14. Now it means that I can now call for the pay. Okay, and these values will be the values for what? Amount paid for insurance from what? State 14. It's 169 observations. Okay. So the box plot you saw here, which is state 14, will be somewhere here. I can now plot it on its own. Is that okay? So let's see. So I can say box plot. Oh, what have I done? Box plot paid. So these are the payments. There it is. You see, it looks similar to what you see in there. So they are observations. So now I can now check whether this one follows a normal distribution. Can I say that it follows a normal distribution? Are you sure? No, it has so many outliers. All these, remember our discussion on the box plot. All these are outliers. That's why, for example, the assignment I gave you, I want you to check whether they have the same average payment. You don't just start with the test. You have to describe them. How does um, the 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 various states, the payment within the various states, how are they? You can even put all of them together, get the street statistics on all, and talk about them. Then before, that's how you write a report. You cannot just jump straight into the inferential statistics. You must provide some description of the data. so that people understand how the data is before you move on to fit any model. Okay, so let's see. You said you weren't here, so that's why. Last week. Yes. Yeah. And the other one, the SOA. Okay. So it means you have to present. If you don't present, I won't know what you have done, whether it is right or not. So please, you have to do so. And I have, I'll, okay. So you remind me, I'll put a sample of the work that they have done previously on it so that you see how you have to do this. Okay. So look at this. Even if you don't know what the test is, you know about p-value, right? Okay. But this is a test on normality. Okay. So this one, look at the p-value. We'll reject normality straight away. Okay. So you see, pictorially, we can see that this does not follow normal. Then we do a formal test to show that this doesn't follow normality. So it means that in your assignment, there's no need to use ANOVA, but rather what? A Kruskal-Wallis test. Because the assumption of normality is not satisfied. Also, they do not have equal variance. Is that okay? So that's it. Now, what it means is that, you see, how many? There are 17 of them. You cannot be doing this 17 times to be able to do it. Computers are good when it comes to routine stuff. Okay, so you go to a factory, a bottle needs to be what do we call it? It needs to be bottled. I mean, that one you don't employ someone to be there because you can get a machine that will do it maybe faster and won't go for break unless it breaks down. So that's it. So when you are doing something that is routine, you don't need to be interacting with the computer. Okay, so for example, when I'm doing some of the things that I do, even our desktops over here, they are quite powerful. So we use it for simulation. So it means that I send my work to the lab, and then I go my way. So maybe in a day or two, depending on how long it takes, I check my email or I check it. So I don't need to physically go there. Okay, so if the thing is running for a day, you don't want to come back and now come and key in something. You automate everything, and then it works. And then by the time you come, you have your results. And so forth. So that's the sort of things we're trying to do. Okay. So what I mean is that if we want to go to now state one, it means we have to change this. So let me use this. So if I want state one, or let's say 12. I have to change this to 12. Then I come here and I change this to 12, right? Then I run it. Okay. So it means if I go and check now, if I display head of state 12, I'm also going to get another set of. So are you going to continue this till all the states? No, because it's routine. It's like the same thing. You are just changing certain things. So what that leads me to what we call apply family of functions. So functions are very good, and that's why we took time to go through it. Now, once I teach you functions, I can even not meet you again, and I have taught you, right? Because the rest is up to you. Okay, all you need to know is that this is how a function is written. Okay. This is how you use a function. So when we take the life contingencies, all we are going to do is to take functions from there and run it. So I know that a function will contain an argument. Okay, so once you know how to get input in the argument, then you go. That's it. Yeah. So my level 300 students, I didn't really, because I taught them in 200. And yeah, but I mean, they picked up. So as and now, I don't meet them. I meet them like what? What maybe like a week or sometimes 2 weeks. Okay. Because once you have the basis, that's it. move on. Okay. Now, let's look at this. Let's type apply. Now, why are these functions important? They are important. And by the way, there's a video on it on YouTube. If you go there, if you check, there's apply family of functions. So I'll add this as well. There's a video on it if you can watch it at your leisure time so that you get more. Because it may not be the same the way I approach it. But basically, they are the same thing, just that you have different examples. Okay. Now, you see, when I have a data frame or a matrix, I may be interested in applying a function, maybe row-wise or column-wise. That's what I'm talking about, routine. So let's say I want to sum each row. I don't need to now go in and select row 1, then I sum, then I select row 2. So if it is 10,000, what are you going to do? That's why programming is good. It comes in handy because then you can then automate it. Just one line of code, everything will go on. So for example, you know what a contingency table is. What is a contingency table? Contingency. It is. I said contingency table. It has rows and columns. No, you are talking about live table. Okay. Um, can you continue with that? I think state.x77. They have a okay. You can assign the rows. State.x77. Yeah, or maybe that memorization. I think state.x77. Okay. I think it's in start package. So just do question mark. No, it's not really. Yeah. Please, I'll be back. So setting this
So this one is we are using state.x77. Do you have this one? So you go to datasets package. So you go to packages, and then you find datasets. Are you all there? Okay. So it is a matrix of 50 rows and 8 columns, giving the following statistics in their respective columns. So there is population, income, literacy, life expectancy, MEDA, HS grad, frost, and then area. Okay, so that is, we are going to use that data. Okay, so we can view that data set. So we can use view and then we run. So this is a brief overview of the state.x77 data. There is the population, income. You said, but do you all have this? So you have population, income, all the way to area. Okay. There is Alabama, for each of the states, I think 50 states. Okay. So it's under data sets. No, it's a base function. So just type VI, or you can just click on the environment. Okay, so type VIN, capital V, view. Okay, so it gives you a spreadsheet kind of view of a matrix. All right. So if you want to see a spreadsheet view of how the data is, you can use that function there. So we have it here, population, income, all the way to area of 50 different states in the United States. Okay. So we are to use the apply. So what do you use the apply function for? We can use it to return a vector or array or list of values obtained by applying a function to margins or an array or matrix. So we can come down and see how it is used. So X can be a matrix or an array. It's an array, but it includes a matrix. And then the margin is a vector giving the subscript which you want the function to be applied. So do you want it to be applied on the rows or on the columns? And then the function is there. So what function do you want to apply? Do you want it to be a mean or whatever? You can use that function there. And then there are many other. The two dots mean you can input your own, arguments. And then the simplify. So there are, yeah. So let's go down. You can find an example here. Okay. So let's look for. Okay, so this is how it is. So we can copy that, then you paste it here. So our data, okay, we don't really need this simplify, so we can take it off. And our X is what? What is our X? It's an array, including a matrix. So we can put our, here is what? State.x77, okay? And then the margin is a vector giving the subscript which the function should be applied over. So when you look here, we can apply the function over columns and rows. Okay, so you can select whichever column you want or whichever row you want. Or if you want it to be, you want the function to be applied over the rows or over the columns. So if you want, for instance, to know the population, income, illiteracy, and everything of all the states, the 50 states, you can do it rather than doing it one by one. So as Dr. Minka said, it is a routine. So you can apply it once and then you have all of them at a go rather than doing it one by one. So for instance, let's see. So we can find the average population or average income of all the states at a go. Okay, rather than say find population. So let's take population. and you can add all the states, the population of all the states, and give us an average. And then we can now go and do the same for income. So the average income for all of the states. You can also do that for illiteracy, but it's going to be one by one. You can do it for all of them so that it will give you probably a vector containing the averages of all of them. You can also do sums. Or you can do sums, you can do averages, which is mean. So there are many things you can do with the apply. Okay. So, okay.
So, yeah, sorry. So this is data on, as you can see, if you do the health files for this, it's some states in the US and it's talk about population, income, illiteracy, and so forth. Okay. Now, you remember you said that a contingency table will contain something like this, and then you have totals at the either rows. So it means that if this one is not really a contingency table because I cannot add income to illiteracy. Did you get it? A contingency table will be categorical variables over there and there. So this one we are just using it to practice. But in real life, you are not going to. Income will be in dollars. Illiteracy rate will be maybe in percentage. So you cannot add dollars to percentage. Do you get what I'm saying? Yeah, so this is just to illustrate that you can find row, something concerning the row, and you can find something concerning the columns. Okay, so I'll start first with the total. So total means you are summing, right? So in R, we say sum. So assuming that I wanted to get a sum of each row, I don't need to go and select row 1, row 2, row 3 until I get to the last state. It's what we are trying to do. Okay. So now what I'm going to do is that I'm going to use apply statement. But before I do that, let's look at it. There is row sum, row sums. Form row and column sums a means of what? Numeric arrays or data frame. So what we are going to do, I can equally use this to do it. But this is going to give me only row sums. So it's going to give me rows are what? States, right? So you see states this. So the first one will be the state with A, Alabama, this, which means it adds all the values within the row, right? And then gives you the total. Once we have row sums, then the composite will be what? Call sums. So we also have call sums. Call sums. So this one, we are going to get what? This is proper because now you are only adding illiteracy rate, income, and so forth. But the other one, it's a non-starter. Unless if we want it, we need to standardize them. If we standardize them, then we remove all the rates from it, and then now we can talk about values that we are summing with the same unit. So this one, you see, population. So this will give us population of what? All the states, which is US, right? And then income from all the states. Illiteracy, right? It means about 58.5% are literate, right? Oh, no, are illiterate, if I should put it that way. Life expectancy, like that. Murder rate, HS grad, frost, and area. So that's better. Okay. So these are just, some. What if I wanted a product? Or what if I wanted to get a function that will describe each of the data? Remember we use describe, right? Okay, so what if we wanted describe? I cannot say call describe because that's certainly not a function in R. That is where the apply functions comes in. that I can use apply and call any function to act on either the rows or the columns. So now what we want to do is that we want to describe each column, right? Okay. So then we will use apply. So the apply, and that's what you were trying to do. Apply has X as an argument, it has margin, and it has what? Fun. X is what you are dealing with. Okay, in this case, state.x77, right? Which is that one. The margin, it takes two values, either 1 or 2. If it is 1, it means whatever you are doing relates to the rows. If it is 2, it means it's for columns. Is that okay? And then the fun can be any function that you want to do. So the first one I'm going to do, I'm going to use this same expression, but I want to use the sum. Then after that, I'm going to use describe. Okay, so we see what happens. So x will be state dot x77. Okay. Now margin will be 2 because we want to deal with what? Columns. Is that okay? Then the fun, what fun do you want to use? We say sum. Okay. Now let's run this. You see, we got the same thing as we use the call sums for. Okay. Now let's go to site. Remember we did this, right? We installed this package, right? Site. Remember there is a function called describe in there, which gives you descriptive statistics, right? Okay. So now, what if we want descriptive statistics? So this is descriptive statistics for each word, for each variable. Descriptive statistics for each variable. Now, so it means I'll just copy this, right? And instead of sum, I'm going to use what? Describe. And I take off that, and that's it. So now if I do this, there it is. So it takes each, let me do it this way so that all of them will be on the same line. Oh, still it couldn't, but it's okay. Yeah. So the first one, population, the very number of observations, 50. The average is this, the standard deviation, the median, the trimmed mean, and we talked about it. Mean absolute deviation, minimum population was 365. Okay, maximum was 21,000. So and so. The range is of course the maximum minus what? The minimum, right? Okay. And then skew. So the skewness is 1.92. So this is positively skewed. Is that okay? It is positively skewed. Yeah. No, margin is cap. You see, R is case sensitive. So even the X is also capital letter. So if you usually to avoid this thing, you always use the question mark to call the function. Then you insert in the values. When you start writing, or when you start writing within the function, it will come there, you select. Other than that, you find those problems. Okay. What else? So if I go down, it will be the next one, income, right? I'll get the distributive statistics on income and so forth. So it means that I can call any function, a group of functions, to work on such things. So let's say I have claims. You see the claims data that you are dealing with. Okay. if you each state will have a claim data set, you can work on each of them if you organize it in a data frame like that. Okay. So that's it about the apply function. There are a couple of them. There's lapply, there's sapply, and so forth. Is that okay? Now let's see what happens. So okay, so you do your own example where now I want you to plot each column. I want you to get a box plot of the variables. How are you going to do that? How are you going to do that? For each variable, I want you to get a box plot of the responses from the state. Yeah. So you are going to do that for all of them. Yeah. That's it. What you are doing, we have to do for each of them. That's what I'm saying we should avoid. When you try, no, you have to scroll back. Because it's plotting also, how many columns? And the object, once you see object not found, it is either you have not defined it, and you have not loaded it. So for example, you is side has been loaded. Side. So you have to go to facilitate side. Then when you describe function is inside. So then you go to rerun your phone, you get to the side. No, it's P like psychology. And then now you rerun your phone. But the describe is in that side. Have you been able to get it? So you get everything close. You have to scroll over. No, they won't count on one. So go over. I always say, if you go all of it, that's the life of people. That's like that. Yeah. So if you do this one, one, two, three, scroll back, you will see it of them. As I said, you are doing box plot. Box plot of all the variables. So you see, first one we computed discrete statistics. Now instead of discrete statistics, we want a plot which is So the function that we are going to use is box. So you copy the table, then you are going to change the fund right. So you need to take out those parentheses. Taking the other good and now run it. So you see that they are sorted about depending on the how many, so many of them. So if you scroll back, this is the last one. If you go back, it's the second, the last one. And that's yes. No, it means for each column, the first column is added population. Create the first column for it. Then you move to the second column. Then you create one. So it's like you are doing what of all the so there is a routine. Like just repetition. So it will do it just one and that. So that's the thing.
Assuming that if we had kept, let's say, bar from
Yeah, but this one is
if you
not.
don't look artistic,
Yeah, but this one, the variables are quantities. Now we can get histogram or pie chart. Pie chart will go over histogram. Yeah, histogram. So this one, the function just means. You can get it once if you want to try.
I don't know, this is
This one. You will have
states the X means
yes, it's a data. It's an input.
so it doesn't change over time.
No.
It's depending
So
on
there's someone data that they collected some years ago.
just for specific purpose. Now you can I was thinking like this time.
So can we move on? Okay, so you see how this can help. Okay. Now, so what I want to state is that when you take your insurance, the auto claims, okay, and okay, let me show you. Now, what were we trying to do? We were finding the Shapiro test, right? For each state. But it meant we have to do this over and over and over again. That's why we were treating the apply statement to help us to overcome that. Okay. Now, I can say state.vec is this. That factor. You know what a factor is? You know what a factor is? A factor in R. Okay, so actually I should use levels. So a factor in R is used to represent, okay, yeah, is used to represent categorical data, but it helps you to be able to state whether it is nominal or ordinal. So if you look at this, this is a nominal data. Okay, but I can factor and and arrange it, ordered, and then it becomes an ordinal data set. Okay. Now, so the state that we are dealing with, okay, there are levels of it. Remember that we have almost 6,007 something. So each of them will belong to one state. So if I want to list it, you see, I was listing the state. You see, it cut it off around 1,000. And it tells me that there are 5,000 omitted because other than that, it will clutter the whole space. So it displays some for you and then it takes out the others. Okay. Now, so if I use levels, now I have all the levels of the state. So there's state 01, state 02, state 03, up to what? State 17. Okay. Now, remember what we were doing. What we were doing earlier was that we go to a state, where is it? This one, auto claims, right? Like this. But I said we have to repeat this for 17 times. You don't want to be doing that. Okay. So if I want to get like a list, remember this will be data frame. So if I want to organize it, it cannot be a data frame. The only thing we treated that can contain other data structures was a list. So I can have a list that contains a matrix and it contains a vector, it contains even a list within the list. Okay. So what I'm going to do is that I'm going to use the counterpart of this apply statement called L apply. There's also S apply. So what I'm going to do is that this state has levels, right? Level 1, level 2. So when I take it, I'll put that over here. And then I'll be able to now separate them into data frames, okay, for each state. So this is how I'm going to do it. I'll call L apply. This L apply can act on my state vector. Okay, then, so this one doesn't use margin. It's just X and its function. So so L apply, let me show you. L apply. You see, it's a list and then a function. Okay, but I want to get a hell file, so I'll just call this off and use L apply. So it says what? L apply is in base. Apply a function over a list or a vector. So what I'm going to do now is like a vector. You see, this is a vector, right? State.vec is a vector. So I'll say state.vec. If you take state.vec, the first one will be X. So it takes each object in this list and then pass it through this. So I'll say X and I close it. So what is happening is that now if I take state.vec, I pass it through this, then I select a function state.all. So I'll call this state.all. Okay. So now if I look at state.all, let me use structure of that. You see what it is? Now, okay. So let me look at it here. It's quite big. State.all. You see? So it's a data frame. So it contains several data frames. The first one is a data frame, 166 observations. The second one is also a data frame, 1,122 observation. Do you get what I'm saying? So what is happening is that I have now separated all the information. There were 6,007. I have grouped them according to the states. Okay, with just this line of code, that I get the levels because I want to deal with states. So I separate them into what? A vector made up of all states. Okay. Then I say for each vector, so take state 1. You pass it through this as X, right? It is the same as going up there and writing auto claims, state is equal to state 01. Then I come, I do state 02. I do state 0. It's routine. You are just doing this over and over and over again. So what I did was to now do this at a go. Everything, yeah. And now I have a list. That list, the first one is a data frame. It contains only state 001. So now, if you remember our discussion on list, I can call this state.all and say 1. So if I display this, it's going to display only, you see state 01, state 01, see, all of them will be state 01. If I, 2 will give me what? State 0, so there it is. You see, state, all of them. So the 32nd observation is state 01. Then the 33, 38, 43, 128, and so forth. Remember, in the state of S77, they are not organized in the states, are messed up. So they help us to what? Segregate them into the individual states. So that's how powerful these apply families are. Yes. 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 So this is like you are querying a database. Exactly. Yeah. So you have a database in there. You want to maybe you have, let's say you in your company you have regional subsidiaries. They all bring their data. Now you want to work on Ashanti branches. You want to work on this branch. Then you should be able to select all customers from that branch. So the key you are using to query the database is the branch code, like that. So here we use the state to do that. What we have done, as I said, you can have other functions that you can use to do, like subset, okay, like width, and so forth, which will make things easy. But apply is quite powerful. There are so many of them. You know, when you are doing programming, sometimes these ones they go one after the other. Okay, but when you are doing a lot of codes that involves repetitions, estimation, and so forth, you can't be doing that. So you can even have par L apply, which means the computer's core, you know, the cores, now you have maybe 5 cores or 7 cores. Okay, Windows is not good at that, but the Unix data, Unix, maybe Mac OS will be able to do that. That you can actually call the cores, okay, so that it does it. Every core will be taking part, and so that it runs faster. So this for those of you who will probably continue to do PhDs and so forth. Sometimes when you have to do simulation, it takes time. It takes so much time. When I was doing my PhD, especially those in physics and biochemistry and so forth, some of their simulation lasts for more than 3 months. Yes. Yeah. And civil engineering. Yeah, and so forth. Because sometimes you set up an experiment, like those that build stadiums and this high rise, before they before they dig the ground and so forth, the concrete, they have to take samples and come to the lab and subject it to all the weather conditions. As for here, we have one weather, but So they will do it, and then its counterpart is on the high performance. They call it HPC. So they will be running it, and so quite an interesting thing. And once you send your work, you have to time it to see if it's a day. There's a day because the shorter one will get priority. If it is long, it's in the queue. Yeah, and so forth. So yeah, but you can use this apply statement to share your programming along the course that you have even on your laptops. So the MC is it NCL apply or something? Yeah. So multiple cores L apply. But it doesn't work on Windows. Windows, if you give it even 4, it will still be using one core. But if it is Unis and what again? Mac, yeah, it will distribute it among the cores. So it works faster. So if you have 7 cores, your Windows will be using one core to be doing your computation, whereas these ones are using 7. And so yeah, so that's the beauty of this apply family. This you just have to continue with it. We can, but at least I've shown you how this is done. Pardon me. Okay. Okay. When you are in a car, then they can. So they are looking for you. Uh, but the zoo is it really there? Where do you pass to go there? Because the signboard was there, airport something something, and I mean it's not there. Yeah, before the Benam, yeah, on the left if you are going this way. So and people go there to look at it. But what about the one around the Lima? Yeah, no, those people. Why are you saying women? The men to go. You are in statistics department, so everything you do mathematics. Oh, okay. Because my kids have been worrying me, but I didn't know they were there. But there was one that I'm confused. You see, when you pass through TV, before TV3, that one, are they still there? They are no more there. So they sold the land now. No, they actually, yeah, the forest, yeah, they did. There was a signboard over there. But I didn't know that. Somebody will find it. Yeah, they will chase it. Said they have dogs too. But this one it will catch the dogs soon. Anyway, let's do let's continue. So that is for the apply. And please go through the video as well to help with on this. Okay. So what else? Now let's come. We've done functions, right? Okay. So now I think we have the basis to now take packages and be able to work with them. Okay. Now, so if you look at what I posted on your WhatsApp platform, is somewhere, it's actually a paper that somebody did on the actuarial package. So it has a vignette, but this gives you better examples in it. Okay. So you're going to work through it. I'll just go through some parts with you, and then the rest will be up to you to. So look at section 4.2. Okay. So if you look at section 4.2, maybe I should display it for those who do not. Section 4.2. So this is life contingency table. Sorry, life contingencies package. And these are So it even has financial mathematics and so forth. That's not what we set out to do. So I'll skip, but you can practice it. It means all those functions are part of the package that you can use. What we are interest rate, you can create amortization table, okay, and so forth. Present values, cash flow analysis, net present value, internal rate of return, and so forth. So my undergraduates, they do financial mathematics, so they are actually doing this as we speak. But what we are interested in, so these are loans and so forth. So it's quite a nice paper and quite easy to work on your own, the duration and so forth. But these are financial mathematics. So then, analysis of light tables and actuarial tables. Okay. So here, before we get here, let me show you something that oh, okay, yeah. So all these are all your life contingency stuff. Okay, so yeah. So TPX, right? You have if you read over here, statistical and financial foundations of life contingencies. So we have life, okay, at time 0, number of people, then at time 1, it will keep on reducing if we want the life table. So we get to omega, which is the last time everybody. I mean, the last time, sorry, the last person to die, right? The age of the last person to die. Okay. Usually maybe 100 and something. Omega is 90, isn't it? Okay. So TPX, you see, is what? The survival probability, right? That the policyholder is alive at age X and will reach at what? Age X plus T. TQX will be the complementary, which is that you die, right? So forth. Then TDX will be the number of deaths between some A. So if we have just DX, then it's the number of deaths within X and S plus 1, like that. Okay. Remember, we can have the deferred mortalities and so forth, all those things. TMX, the central mortality rate of ages. EX is the curtailed expectations and so forth. So these are all your life table stuff. Okay. And then when you come here, you have examples of contingent insurances. Okay, so any year term life. Okay, the actuarial present value of Z like that. Okay, then you can have life annuity, benefit paid out, I mean, insured survives, the actuarial present value, and a pure endowment. Okay, you only gain something when you survive up to N years. Any endowment insurance will pay days, and so for the actuarial present value, and so forth. So you can get all those stuff in this package. Okay. So please go through it, and then we go to 4.2, which is a life table. Okay. So how does this look like? Well, there are functions to do all these things for you, but these are inbuilt functions. And because you do contingencies, life contingency, I expect that you should be able to write a function to do what all these functions are also doing. Okay. Now, how do you Of course, you have the mathematics behind it, so you can do it. But I'll show you how this um there. So look at this. So let's say ds2, dst. So this is the function dst in R. Okay. So it may look so simple. What is dst? If I go back, it tells you there's between age x and s plus t. So if I give you a table and you are finding this, how would you find it? Yes. Yeah. The difference. So it's quite simple. Okay. But in now it is not that simple. The reason is that it must rule out all the things you cannot do. Okay. Yeah. So essentially, if we look through it, we will see the core place where it is actually subtracting. Have you seen here? You see ls minus something, but it has to take out all the things. For example, you cannot get negative, right? And so forth. So that's it. Okay, so that's what we should be looking out for. Okay, so yeah, so that's it. So if you are writing, you can write such a simple thing to do it, because the key thing is that you are subtracting the lives alive at lx, okay, minus the case where you have ls plus t. That's it. That's the main thing, and so forth. Okay. But you know, R doesn't. R will take a data frame called live table before it does all. That's why you see so many things in there. But it's up to you to be able to spot where, because you know the mathematics behind it. You know when you know how programming is done in R now. You know where exactly the actual computation is being done. So forth. Okay. So let's see. So there are so many functions. This is a survival probability. PXY is survival probability between or more lives, TPXY. KOST is the death probability between X and S plus T. KOST, death probability for more lives. TXT, number of persons years lived after exact age X. Okay. MXT, central death rate. QF2MX, convert death probabilities into mortality rates. M2, this one, death probabilities. EXN, expected lifetime between what? Age X and X plus N. Okay. Our life, sample from time until death distribution, underline a life table. So all these are to help you to be able to, for example, price an insurance for a life, age X. Okay, and so for props to live table ls from raw one, and so forth. So these are functions you can find to do this. Okay, now so I would treat live table and actuarial table as classes. Okay, so what we are going to do is that if we have an actuarial table, it inherits what? The live table. Why do we need live table? Because it helps us in what? Pricing insurance. So how do you create a live table here? They have enumerated three methods that the three components of this live table. So the year sequence, okay, which will be at time 0, where the lives, maybe 100,000 of them will start at age 0. Sorry, not age 0, but at time 0. Then year 1, you check how many have died, you record. So your L1 will be at least either it is equal to L0 or less than that. And then you continue until you follow them till they die. And that's why we don't have one here, because nobody has that time to follow and the resources to follow people. So you go and take one from South Africa. But the way they eat the way they live their life, and so it's completely different from us. So, and that's why we are here. That if we know all these things, then maybe later on when we take positions, we will now say, okay, we have to also create a life table for ourselves if we want to grow our market. Other than that, you sit over there, you have to conjure things to be able to get a premium for your will-be policyholder to pay. So forth. Okay. Now, so ALS is a vector, and then also you have the name of the life table. So how do you create the life table? There are also enumerated 3 ways directly from S. Essentially, if you want a life table, what you need are just the S and the LS. The rest you can compute it from, because all of them depends on those two information. So once you have that, you can create it. Or if there's already a data frame already there, that is a life table, you can also create it from there. And then also, if you have the raw survival probabilities, you can work your way back to get the X and LS, and then you create your life table. So that's it, what you can do. Then creating a life table. So we can analyze this and see how this life table. So the first line of code, what does it mean? This one. Let me increase the font size. What does this mean? The first one. Remember, I said the R with that is not necessary. What does it mean?
Data from 0 to 9, increasing by 1 to 9.
Okay. And then? Yes, you haven't finished.
0, 1.
And then? You name it as example. That's it. Okay. So if I copy this, now you've told me what it is. So it means if you want to, you must understand what is it. If you don't, then you run and see. But essentially, by this time, you know all this, and you should be able to understand what we mean. So this is nothing more than S example will be 0, 1, 2, 3 up to 10, 9. So how many observations? 10 observations. So it means we are going to create our our life table. It will be made up of only 10 observations. Okay, so let's go back. So with this, you should be able to go through this. Then remember, we need LS, right? So now we have LS will be the number of people. So this one is a vector, right? C is a vector. So we started first with 1,000 people. We are assuming that year 1, 50 died, 950. Then 100 died the second year. Then 150 died. Then 20 died. And then 80. And then 50. And then 150. And then 200. And then 150. The rest we stopped it at that. Okay, it means we can. So let's see. We do this, but at least all of us understand this, so we can. If we want to display our example, we get something like that. Okay, all right. Now here, this is where but here you must have, that new is a function in life contingency. Is that okay? Okay, so life contingency will now help us to create a life table. Remember, a life table should consist of S, LS, the probability, the death probability, and even the expectations. That will give us a complete life. And then we can compute other things. So what life contingency will help us is that we will be able to create a life, what is it? A table. Okay, so let me copy this, and then we go here. Okay, so I'll paste this. Remember, I said the plus is not needed. In the book, it is telling you that this is following the other. Okay, so we take it off, and then let's analyze this. So new life table so that it gives us the characteristics of what? A life table. So before you're able to do this, you must have your life contingency package clicked or ticked. If it is not ticked, you won't be able to use the function new. So life. So you see mine is ticked, right? Okay. So we are creating a new life table. X is X example, which is the years, right? So that will be 0, 1, 2, 3, up to 9. Is that okay? Then we need the LX. LS is the number of people. That's what we said is what? LS example, right? Okay. Then the name, we say example live table. Okay. So let's run this. So we run it, there's no red marking. So it means this has created a live table. Let's go to environment and see how this looks like. So look at its name. Example LT says of former class live table. So live table is a class in R because we have used the live contingency to create it and so forth. So now we can check how this live table looks like. Let's display it. There it is. So it says live table, example live table. Its name was what? Example live table. Remember, we named it what? Example live table. Okay. So X, at year 0, there were 1,000 people, right? Then at year 1, there were 950. So this is your 1px, right? So just px. Okay. So we can get all those probabilities. Okay. So this is Lx1 over what? Lx. Or L1 over L0. That gave us that one. That one will be what? L1 over what? Sorry, L2 over what? L1 and so forth. So that's it. That's why I said you can create this on your own. Is that okay? But life contingency gives us an easy way of creating all this. Then we can get the expectation of X as well. So if you look through you should know how this EX is also computed. Remember, you can also do it in the table that I showed you, EX, expected lifetime. But this one, it means it's N is 1, right? So we just have E at just, because they are just following 1 year at a time. But of course, we can start from 1 to, let's say, the 7th year and find the expected lifetime and so forth. So that's it with the contingencies. So there are several examples in there which you can look at it. So there are some life contingencies, life tables already in R through the life contingencies. Like if you check page 24, there is AF92LT. That is the UK AF92 life table. There's also UK AM92LT as well. It's also from the UK AF92 life table. Yeah, then you have demo ETA, which is the various Italian live table, including RG45, IPS 55. The demo USA will be the US Social Security live table and so forth. As I said, we don't have some, right? And so forth. SOA, the SOA illustrative time live table and so forth. So you need to go through it and go through some of the codes and see how this is done. So survival probabilities, if you create a live table, I can ask you to compute the survival probability. Okay, maybe for male and female, and be able to comment on it and so forth. So there's actuarial table as you get to 26 and so forth. So this is your assignment you have to go through, because I'll ask you some of it in your exam. So please, demographic examples. You see, in your exam, they have examined you in your life contingencies. What I'm checking is whether you can implement them in a. So that's it. So now that you have the basics, you know how to use functions, you know how to use packages. I can give you a data set. I say create a live table. You should be able to do it. And then answer some questions concerning it. Because all the functions are available to you. If I ask you to compute the expected expectation, you should be able to do that. So I think that should be it for today, unless someone has a question. Is everybody okay? So can you submit your assignment this week? As I said, you can do it groups of maximum 3. If you want to do it on your own, 3.
But the presentation, especially that of last week, we haven't
Oh, okay. Let me even stop it. Sometimes I think one of them I did not stop it and it took like 6 hours. Now to